The last section in Chapter 11 is 11.7, Cylindrical and Spherical Coordinates. So far, we've been using what's called a rectangular coordinate system, where points in space are located by coordinates x, y, z. Our objectives are to use cylindrical coordinates to represent surface in space, as well as using spherical coordinates to represent surfaces in space. For the cylindrical coordinate system, you have a point in space that's represented by an ordered triple where the components are r, theta, z. R, theta, z. That's going to be in place of x, y, z. This is similar to doing polar graphing in your previous, probably pre-calculus class. You did polar. Well, this is similar, but was now extended to space. R, theta, z. R theta is a polar representation of the projection of P in the plane, in the xy plane, and Z is the distance from that point in the xy plane. So this point that's located x, y, z is now where you would go from the origin x units, y units, and then up z units. Now we're going to go out a radius, an angle from the positive x-axis in the direction towards the y-axis, and then up z to get our r, theta, z, the position in the cylindrical coordinate system. Now recall, these are some of the conversion equations we used when dealing with polar coordinates. X is equal to r cosine theta and y is equal to r sine theta. You can see that in the picture we have this triangle here where x and y are the legs of a right triangle and the radius is r. So using the Pythagorean theorem, this leg squared x squared plus y squared is going to equal r squared. That's our conversion equation for cylindrical coordinates. If we know x and y, use the first equation, r squared equals x squared plus y squared to find r. To find the angle theta, if you know y and x, and the tangent of that theta is the opposite over the adjacent. Tangent theta is equal to y over x. And then the conversion for z is simply just z. So you would find the inverse tangent of y over x to find the angle theta. Again, these are the cylindrical to rectangular coordinate systems. X equals r cosine theta, y equals r sine theta, and z equals z. From rectangular to cylindrical, r squared equals x squared plus y squared. Tangent theta is equal to y over x, and z equals z. For this example, we're going to convert from cylindrical to rectangular coordinates. Convert the point r, theta, z, which is 4, 5 pi over 6, and 3, to rectangular coordinates. You can pause the video now and use the formulas, those conversion equations, to find the points, the point with coordinates x, y, and z. Okay, so by using the first equation, x equals r cosine theta, we can see that x is negative 2 square root of 3. Y is r sine theta, and when you simplify that, you get y is equal to 2. And then to find the z is equal to 3. It's simply the same value in both rectangular and cylindrical. Now this is what it looks like by graphing it. The point with cylindrical coordinates 4, 5 pi over 6, and 3, imagine going out 4 units, but the angle that you make from the positive x-axis is 5 pi over 6. From the positive x-axis to the direction of the positive y-axis, you're going to have an angle of 5 pi over 6. You're going to go out 4 units in the radius and then go up 3 points to point P. Now, what's a good idea to check to make sure your converted coordinates will bring you to the same location. In rectangular coordinates, you would move negative 2 square root of 3, you would move, okay, so back in that direction, you would go over 2 units and go up 3 units. So it would bring you to the same location in both cylindrical and rectangular coordinates. Here are some examples of surfaces using cylindrical coordinates. And cylindrical coordinates are especially convenient for representing the cylindrical surfaces and surfaces of revolution with the z-axis as the axis of symmetry. This is our first equation is a cylinder, x squared plus y squared equals 9. This can be converted to cylindrical coordinates because the conversion equation for x squared plus y squared is equal to r squared. We end up with r squared equals 9 or r equals 3. For the paraboloid, the equation of this particular paraboloid is x squared plus y squared equals 4z. This can be converted to in cylindrical as r equals 2 over the square root, 2 times the square root of z. And x squared plus y squared is r squared, so you would get r squared equals 4z, and you would take the square root of both sides to get this converted equation for the paraboloid. A cone is represented simply with r equals z in cylindrical coordinates, where a cone in rectangular coordinates is represented with x squared plus y squared equals z squared. Well, by using the conversion equation for x squared plus y squared, you get r squared. So if r squared equals z squared, then r must equal z. It's a relatively simple formula in cylindrical coordinates for a cone. And then for a hyperboloid, we have the hyperboloid x squared plus y squared minus z squared equals 1. Using the conversion equation for x squared plus y squared, we get x squared plus y squared, which is equal to r squared. So that would be r squared minus z squared equals 1, and by writing this as r squared equals z squared minus 1, we get the cylindrical representation of the hyperboloid of one sheet. Vertical planes containing the z-axis and horizontal planes also have some simple cylindrical coordinate equations, such as the following. Here we have this vertical plane that goes right through the z-axis. It can be expressed simply as an angle. The angle that it makes from the positive x-axis in the direction of the y-axis is that angle theta, equal a constant. A horizontal plane in cylindrical can be represented by z, which is equal to c, some constant.